How to design a rate limiter. Let's explore the process of designing a rate limiter step by step to control API requests and protect your system from overuse or abuse. 1. Why do we need a rate limiter? Without a rate limiter, users might overwhelm your servers by sending excessive requests, cause performance degradation or even downtime, exploit your system through DDoS attacks or bot activity. A rate limiter ensures fair usage and protects your resources by controlling the number of requests made by users or IPs over a specific period. 2. Understanding the problem. Start by defining the requirements. How many requests are allowed? Example, 100 requests per minute. What happens when the limit is exceeded? Block requests, send warnings, or log events. Scope. Should the limit apply globally, per user, or per IP? 3. Choose the right algorithm. Select an algorithm that suits your needs. Fixed window. Tracks requests within fixed time periods. Simple, but can cause spikes at boundaries. Sliding window. Tracks requests over a moving time window, smoothing request flow. Token bucket. Allows bursts of requests up to a maximum capacity, followed by steady rate limiting. Leaky bucket. Controls bursts and ensures a consistent request rate by leaking requests at a fixed speed. 4. Data structures. Identify the data you'll need. User IP identifier. Tracks requests by user or IP. Timestamps. For algorithms like sliding window to calculate request rates. Counters. Tracks the number of requests within a time window. Bucket capacity and refill rate. Required for token bucket algorithms. You can store this data in tools like hash maps for single servers or Redis for distributed systems. 5. Workflow of a rate limiter. Here's the high-level process. 1. Receive API request. Identify the user or IP making the request. 2. Check rate. Use stored data to determine if the user's request count exceeds the limit. 3. Decision. If under the limit, process the request and update the tracker. If over the limit, reject the request and respond with an error or warning. 6. Handle concurrency. If your system processes multiple requests simultaneously, use thread-safe data structures, e.g., synchronized objects. For distributed setups, use tools like Redis or etcd for atomic updates. 7. Plan for scaling. Small-scale systems use in-memory storage like hash maps for simplicity and speed. Large-scale distributed systems use distributed tools like Redis to store rate-limiting data and maintain consistency. Load distribution. Partition data by user or IP to balance the load across servers. 8. Address edge cases. Account for specific scenarios, such as DDoS or bot traffic. Quickly block malicious requests by identifying suspicious patterns. High-volume users allow exceptions for trusted users with higher request thresholds. Distributed requests use a centralized system to maintain consistency across servers. 9. Monitor and analyze. Track the performance of your rate limiter. Collect metrics like request rates, blocked requests, and error rates. Use tools like Prometheus or Grafana to monitor system health and visualize trends. 10. Documentation and improvement. Document your design and decisions. Include details about the chosen algorithm, scaling approach, and edge case handling. Iterate on the design by incorporating feedback and improving performance. Conclusion. A well-designed rate limiter balances simplicity, performance, and scalability while protecting your system. By following these steps, you can create a robust solution that meets your application's needs and ensures fair resource usage.